All right, hello. This is the Chapter 9 to 10 examination, and today I'm going to be doing question 3. Okay. All right, so we'll just start with Part A, and then I got my laptop here so I can read the questions. All right, so Part A says a solid cylinder of mass 12 kilograms and radius 0.250 meters is free to rotate without friction around its central axis. If you do 75 joules of work on the cylinder to increase its angular speed, what will its final angular speed of the cylinder what will be its final angular speed if the cylinder starts from rest? All right, so we're trying to find angular speed, and that's shown by lowercase w. All right, so that's what we're trying to find. And in order to find this, we're going to be using the work energy theorem for rotation. So that formula is work equals 1/2 times inertia times angular speed final squared minus 1/2 inertia angular speed initial squared. And in this scenario, because it says the cylinder starts from rest, angular speed initial is going to equal 0, and so then that's going to mean that this whole part cancels out, and we're only going to be dealing with this part. So what does it give us? It gives us mass equals 12 kilograms. It gives us radius equals 0.250 meters, and it gives us work, which is capital W, and that is equal to 75 joules. All right, and so first off, we're going to have to find inertia. Okay, so the inertial formula is inertia equals 1/2 times mass times radius squared. Okay, and then we can just plug all the variables into that. So we'll have 1/2 times mass, which is 12, times radius, which is 0.250 squared. All right, we just have to solve for that. So let's see, so we got 0.5 times 12 times 0.250. Actually, and that's squared. Okay, so times, okay, so that's 6. Okay, so 0.250 squared equals that times 6. All right, and we get 0.375. 0.375. All right, so that's our inertia. And then once we have that, we can just plug everything into this work energy theorem. All right, so our work is going to be 75 equals 1/2 times 0.375 times work final, which is what we're solving for. And then it would be minus this part, but because this is 0, all this cancels out, so we don't even worry about that. Okay, so then we can do 0.5 times 0. Okay, so 1/2 that times 0.5. So that's going to be 0.1875. 0.1875 angular momentum final squared. And then we can just flip this around to be in terms of the angular momentum equals 75, and then that would be divided by the 0.1875. Okay, so then we can do 75 divided by 0.1875, and that's going to give us 400. And then because this is squared, we just got to square root that. So then we do the square root of 400. And then our work, or not our work, sorry, our angular momentum final equals square root of 400, which is 20. And that's going to be in terms of radians per second is the units for that. All right, and that's all there is for A. Okay, now we'll go on to part B. All right, part B says, what will be the cylinder's final angular speed if it's initially rotating at 12 radians per second? Okay, so this is the same, basically the exact same thing, except now we have an initial instead of it being 0. It's 12, and so then we're just going to have to deal with the other part of this formula. So since we already solved for inertia, it's going to be the same. So we can just plug everything in to the same formula, the work energy theorem for rotation. So it's going to be work, just write out the formula again, work equals 1/2 inertia angular momentum final squared minus 1/2 inertia angular momentum initial squared, and then that initial is going to be the new variable that they gave us. So initial equals, come back, it equals 12 radians per second. Okay, and then we're just going to plug everything in like we did before. So that's going to be 75 equals 1/2 times the inertia, which was, it should be 0.375, and then we're still solving for the final, minus 1/2, and then this is the other part of the formula, inertia, so that would be 0.375 times 12 squared. Okay, so we'll just solve for that later half first. So we'll do 0.5 times 0.375 times 12, so that's 0.1875, and then we'll do times 12 squared. All right, and we get 27, okay? So that's going to be 75 equals, we'll leave that blank right now, minus 27. All right, and then we'll solve for this half. So 0.5, 0.375. So that's going to be 0.1875 angular momentum final squared, minus 27. Then we can add 27, add 27 plus 75, that's going to be 102. So we get 102 equals 0.1875. Can you see that? Okay, 0.1875 angular momentum final squared. Okay, and then we can flip it around in terms of angular momentum. So it equals, okay, so angular momentum final squared equals, and that would be 102 divided by 0.1875. All right, so okay, so 102 divided by 0.1875, and that's going to give us 544. We're getting solid numbers, that makes it easy. Equals 544, and then just square root. And we just need the square root of 544, which is 23.3. We're at 23.3. And then that's going to be the same as the one above, radians per second. And that's it. That's part B. Okay, now we'll move on to part C. Those papers to the side there. Where can you see the top of that? Okay, cool. All right, part C. All right, we're on to a new problem. Part C says, a square plate has mass 0.600 kilograms and sides of length of 0.150 meters. It is free to rotate without friction around an axis through its center and perpendicular to the plane of the plate. How much work must you do on the plate to change its angular speed from 0 to 40 radians per second? Okay, so the thing we are solving for is work. All right, that's what we're solving for. It'll be in terms of joules because that's what work is. All right, and let's see what they gave us. They gave us mass equals 0.600 kilograms. They gave us length equals 0.150 meters. What else did they give us? Oh, the angular momentum initial would be 0 because it's 0 to 40 radian per second, and then the angular momentum final would be 40 radian per second. Okay. Anything else? Okay. All right, so we'll start out by finding. So we're gonna. It's gonna be the same thing using the work energy theorem. So we can just start out by finding inertia. We did last time the formula for inertia. Because it's a square, it's gonna be 1/6 mass times length. That's me. Mass times length squared. Okay, and then we can just plug that in. So 1/6 times mass 0.600 times length 0.150 squared. Okay. All right, so we can do 1 divided by 6. That's 0.166 repeating times 0.600. It's going to give us 0.1 times 0.150 squared. That's going to give us 0.00225. So inertia is going to equal 0.00225. Really small number. You see that? Okay, cool. All right, so then we're gonna do the work energy theorem again. So that's gonna be work equals 1/2 times inertia times final squared minus 1/2 inertia initial squared. Okay, and then we have all of the variables, so we can just plug everything in and solve for work. So work equals 1/2 times 0.00225 times final, which is 40. Right, yep, times 40 squared. And then minus 0, because the other one, the initial is 0, and it cancels all that whole part out. So then we can just plug all that into a calculator. So we can do 40 squared. That's going to be 1,600 times 0.00225. That's going to be times 0.5. That's going to give us 1.80. There we go. So work equals 1.80 joules. That's it. That's all you got to do for C. Okay. Now we will move on to part D. All right. Part D asks. Still see it? Yep. Okay. Part D asks, how much work must you do on the plate to change its angular speed from 40 radian per second to 80 radian per second? All right, so it's the exact same thing, except our angular speed initial is going to be 40 now instead of 0 per second. And our angular speed final is going to be 80 now instead of 40. All right, and we're still solving for work. All right, so work equals, I'll write out the equation again, 1/2 squared minus 1/2 initial squared. All right, and then we can just fill in all the blanks. So 1/2, inertia is going to be the same, so 0.00225. With our new final, which is 80 squared minus 1/2, 0.00225 times 40 squared. All right. All right, we're going to do one side and the other. So we'll do 80 squared, 6,000 times 0.00225, 14.4 times 0.5, we get 7.2. So 7.2 minus 4d squared times 0.0022, yep, times 0.5, that's 1.8, so 7.2 minus 1.8, so 7.2 minus 1.8, that gives us work equals 5.40 joules. All right, that's all you gotta do for that one. All right, we'll move on to a new Percy. Yeah, we'll move on to a new piece of paper. All right, now we're on to part E. Let's line through it. Okay, we got 17 minutes. Okay. Part E says, a hollow cylinder of mass 2 kilograms, inner radius 0.100 meters and outer radius 0.200 meters is free to rotate without friction around a horizontal shaft of radius 0.100 meters along the axis of the cylinder. You wrap a light, non-stretching cable around the cylinder and tie the free end to a 0.500 kilogram block of cheese. You release the cheese from rest at a distance h above the floor. If the cheese is moving downward at 4.00 meters per second, just before it hits the ground, what is the value of h? All right, all that, and we're trying to figure out how high the cheese is above the ground. So we're looking for h. What did they give us? They gave us mass of cheese. Can you see that? Yeah. Mass of cheese equals 0.500 kilograms. They also gave us mass of cylinder. Cylinder is 2.00 kilograms. They gave us the inner radius, radius sub I equals 0.100 meters. They gave us outer radius, radius 0 sub O equals 0.200 meters. And they gave us final velocity, velocity sub F equals 4.00 meters per second. All right, so what we're going to use to find height is conservation of energy. So that formula is going to be mass times gravity times height equals 1/2 mass times velocity squared plus 1/2 times inertia times angular momentum squared. All right, so what do we need to find from that? We got to find inertia. And we gotta find W, angular momentum. Oop, there we go. All right, so inertia. Final inertia is 1/2 times mass times radius, but we have the 2, so radius outer squared plus radius inner squared. All right, we got everything for that. So 1/2 mass is, where was the mass? Which mass was it? We're doing mass of cylinder. Yeah, so 2. Yep, not the cheese. So mass of cylinder, because it's the inertia of that times 0.2 squared plus 0.1 squared. All right, and we plug all that in. All right, so 0.2 squared plus 0.1 squared, that's 0.05, times 2 times 0.5, and we get inertia is 0.05. Okay, now we got to find angular speed. And we can use the formula for angular speed from linear speed. So for this one, it's angular speed equals the velocity over the radius of the outer. Okay? And that's going to be, velocity is going to be 4 divided by the radius of the outer, 0.2. All right, and that's just going to give us 20 radians per second for the angular speed. Okay, and now we can finally plug it all into the conservation of energy, which is mass times gravity times height equals 1/2 mass velocity squared plus 1/2 inertia angular squared. Okay, so we have, and then gravity 9.8. That's another one of the values we have. Okay, so we plug everything in. It's going to be 0.500 times 9.8 times height, which is what we're solving for, equals 1/2 times 0.500 times, where are we at? We're at times velocity times velocity squared, so that's 4 squared plus 1/2 0.05 for inertia times, what was the angular, times 20? Yeah, times 20 squared. Okay. All right, now we can start calculating this out. So we got 0.500 times 9.8. That's going to give us 4.9 H for that side of the equation. All right, and then we can do this everything else. So we got 0.5 for 1/2 times 0.5 times 4 squared plus, or we can just do that. Okay, so that's 4 equals 4 plus 0.5 times 0.05 times 20 squared, that's 10. So that gives us 14, so 4.9 H equals 14. And then we just put it in terms of H. So H equals 14 over 4.9. Okay, so 14 divided by 4.9. And that's going to give us 2.85. If you round all of them, it rounds up to 2.88. is what the homework says. 2.88 meters. Right, and that was for part E. Or 2.86, sorry, not 88. Comes up to 2.86. Bam, just like that. All right. Okay, now we can do part F. All right, so part F says, what do we have? 25. Okay, part F says, what is the angular speed of the cylinder just before the cheese hits the ground? And we already solved that. Angular speed was 20, and that was by angular speed equals velocity over radius, which was 4 over 0.200, 20 radians per second. That's part F. That's all that is. Okay. I'll flip it over. Okay. Now we're on to part G. Almost there. Okay, so part G says, a pulley in the shape of a solid cylinder of mass 1.50 kilograms and a radius 0.240 meters is free to rotate around a horizontal shaft along the x-axis of the pulley. There is friction between the pulley and this shaft. A light, non-stretching cable is wrapped around the pulley and the free end is tied to a 2 kilogram textbook. You release the textbook from rest a distance 0.900 meters above the floor. Just before the textbook hits the floor, the angular speed of the pulley is 10 radian per second. What is the speed of the textbook just before it hits the floor? So, it's like basically the same problems last time, except they gave us height and they didn't give us the velocity. So, what is velocity? Well, what did they give us? They gave us R, which is 0.240, the radius, meters. They gave us the angular, which is 10, right? 10.0 radian per second. And so we can do that same formula that we did earlier, but just flip it around. So we can put it in terms of velocity. So velocity equals radius times angular speed. So velocity equals 0.240 times 10, which you just moved decimal. So velocity equals 2.40 meters per second. That's that. That's all you gotta do. Okay. Last one, part H. All right, part H says, how much work was done on the pulley by the force of friction while the textbook was falling to the floor? All right, so here we're looking for work, capital W. All right, so what do we need for all this? It gave us the mass of the book equals 2 kilograms. It gave us the mass of the pulley was 1.50 kilograms. They gave us R 0.24. They gave us the height. The height was, what was it? 0.9 meters. They gave us the final right there, and then we have gravity equals 9.8. Okay, so how are we going to do this? First we have to find inertia, which is 1/2 times mass times radius squared. We have all that, so 1/2 times the mass of the pulley, so times 1.50 times 0.240 squared All right, so 0.240 squared times 1.50 times 0.5. That gives us 0.0432. Inertia equals 0.0432. All right. And then we need to do, what was the next step? Oh yeah, because we're doing the work energy theorem with friction, and this formula requires initial potential energy. So UI. So we gotta solve for UI. Initial potential energy equals mass times gravity times height, and we happen to have all of those. So that would equal mass of the book. So 2 times gravity, 9.8, times height, 0.9. All right, and if we do that calculation, that'll give us the potential energy. So 2 times 9.8 times 0.9, that gives us 17.64 joules. 17.64 joules. All right, and then we also have to find the kinetic energies of the book and the pulley. Okay, so kinetic energy of the book would equal 1/2 times mass times velocity squared. All right, we have all that. So we got 1/2 times mass 2 times velocity, which is 2.40 squared. Okay, and then we just gotta solve all that. This is also going to be in joules. So we got 0.5 times 2. Wait, times 2. Times 2.40 squared gives us 5.76 joules. All right, and then we have to find the kinetic energy of the pulley. So that's going to equal 1/2 times inertia times angular momentum squared. All right, we also have all of those. So 1/2 times inertia, what did we find it? 0.0432 times angular, which is, isn't that like 10? Yeah, times 10 squared equals. All right, so we can do 10 squared times 0.0432. That's times 0.5. That's 2.16 joules. 2.16 joules. All right. Okay, what's all this leading up to? This is leading up to the work energy theorem with friction. So that formula is going to be the UI, the initial potential energy, plus the, what are we solving for? Work? Velocity? Work times work final equals kinetic energy of the book plus kinetic energy of the pulley. All right, we have all of these but this. So we can do, so then we just start plugging stuff in. So we got 17.64 plus W final equals, right, wait, is it, which W is it? Yeah, it's work. Okay. Yeah, work equals kinetic energy of the book 5.76 plus kinetic energy of the pulley, which is plus 2.16. All right, and then we can add those together. 5.76 plus 2.16. That's 7.92. So equals 7.92. Work F. And then we can just subtract 17.64. Right, minus 17.64. Work final equals negative 9.72 joules. And it's negative because it's working against it. And that's it. That's the whole thing. All right. Hope you enjoyed. See you next time.